Today I am going to present on the topic A star search algorithm, theory, implementation, and real world applications. This presentation focuses on how A star works, why it is efficient, and where it is used in real life. A star search algorithm is an informed search algorithm used to find the shortest path between nodes in a graph. It combines two important approaches: uniform cost search, which considers actual cost, greedy best first search, which considers estimated cost. The key formula is f of n is equal to g of n plus h of n, where g of n is the cost from start to current node, h of n is the estimated cost to reach the goal, and f of n is the total estimated cost. How A star works. A star works step by step as follows. First, we initialize the start node. Then we select the node with the lowest F value. If it is the goal, we stop. Otherwise, we expand its neighbors. We update their cost if a better path is found. This process continues until the goal is reached or no nodes are left. Now we consider a graph with node A to G. A is the start node and G is the goal node. Each edge has a weight representing cost. For example, A to B has a cost 3, A to C has a cost 4, and so on. We will use this graph to understand how A star finds the shortest path. Heuristic values represent the estimated distance from each node to the goal. For example, node A has heuristic value 9, node F has value 3, and goal node G has 0. These values help A star decide which path looks more promising. Now let's see how the algorithm executes. In the first iteration, we start at node A, we expand A and add B and C to the open list. Next, we choose the node with the lowest F value. We continue expanding nodes and updating their cost step by step. As the algorithm continues, we expand nodes E and F. Finally, we reach the node goal node G. The optimal path is found is ACSG and the total cost is 9. This table shows the complete step-by-step execution. It includes current node, g of n, h of n, and f of n values, open and closed list. This helps us clearly track how the algorithm progresses and find the optimal path. A heuristic is admissible if it never overestimates the actual cost to reach a goal. This is important because it guarantees that A star finds the optimal solution. Examples include Euclidean distance, Manhattan distance, zero heuristic, which makes A star behave like this algorithm. A star is guaranteed to find the shortest path. The heuristic is admissible. This works because it always selects the node with the lowest estimated cost compared to other algorithms. Greek star is slower but always optimal. Greedy is faster but not always optimal. A star provides both efficiency and optimality. A star is used in many real-world applications, in GPS navigation systems like Google Maps, in video games for character movement, in robotics for path planning, in networks for routing data, and even in solving puzzles and logistic problems. The time and space complexity of A star is O of B power D, where B is branching factor and D is depth. Advantages include optimal solution, efficient with good heuristic, complete algorithm. However, it can be memory intensive and depends heavily on the quality of heuristic. This is the pseudocode of A-star algorithm. It shows how we maintain open and closed list, update cost, and select the best node at each step. This helps in implementing A-star in programming languages. To summarize, A-star combines the strength of Dijkstra's and greedy algorithms. Admissible heuristics ensure optimal results. It is widely used in many applications and its performance depends on heuristic quality. Thank you for listening.